Okay, now we talk about an example problem. Say you have a plain pendulum and we want to work out energy at different points and maybe the speed at different points when it's motion. So I'm going to work this out as numerical example. Okay, so I'm going to set up the problem so that things are easy to work out. So I let go the pendulum, say at a pretty high angle, say over here, and let's say I let go at 60 degrees like that, and the pendulum picks up speed, and it's over here, some speed, and then picks up more speed, and it's over here. So let's call this A, and this B, C, and this is 30 degrees, say. So we want to figure out if the pendulum length is, let's say 2 meters, then if I let go at 0 speed, what will be the speed here and what will be the speed here? And you can, of course, you can study that and coming back on your own. All right, so we know when the pendulum is moving between here and here, for instance, the force, if I want to compare A to B, I need to make sure that energy is conserved. So I look at something, an arbitrary point here, the tension is that way, gravity is that way, and velocity is that way, which is displacement that way. Displacement and tension are 90 degrees to each other. So tension is a force that does not do any work, which means energy is conserved. So I made sure that this force is a conservative force, and we take its work into account through energy concept. So since tension is perpendicular to displacement, tension does not do any work, hence energy is conserved. So we can apply, if I find what the energy at A is, then I'll have energy at B. This will be one equation, which will be energy at C, and so on and so forth. So we'll apply to this to figure out the speed at B. We can apply this equality to figure out speed at C. All right, so we need to know what is the kinetic energy and potential energy at each instant. So at A, V is 0. That means it's all potential energy. Energy A is all potential energy. And it's actually best to just use this as a zero level, zero potential energy level, and then we can give this guy some potential energy. If you know how much that height is, that's HA, and then over here it will be HB. Okay, so this will be MGHA. Now HA is this whole thing minus this thing. So how much is that thing? So if you look at that thing, and this is theta and this is L, so that's just L cosine theta. So HA is mg L minus L cosine theta, and theta is 60 degrees. So this is mg 2 minus 2 cosine 60 degrees. at B, we don't know what VB is. Definitely is not 0. And HB is not 0. HB is not 0, so we're going to have to write both of them. So what do we have? E at B is half m GV m mgh b, I'm sorry, mghb, potential energy there, plus half m v at b square. And this one going to be same formula except theta is 30 degrees. So this is going to be m g 2 minus 2 cosine 30 degrees plus half m vb square. So now this has to be equal to that based on our observation about how the energy worked. So let's equate that. So EB equals to EA, that gives me mg 2 minus 2 cosine 30 degrees plus half mvb square equal to mg 2 minus 2 cosine 60 degrees. You can see the m's are all cancelled out, so I didn't need to know the mass of the bulb in this example. It was not given from the get-go, and I didn't need to know that in the end. Well, I can see that this 2g and this 2g will cancel because in the same sense this 2 go away. And then I send this down the other side and I have half VB square equal to 2g cosine 30 degrees minus cosine 60 degrees. Now cosine 30 degrees is almost 90% or 87%, so I'm just going to have a simplification here, and this is 0.5 exactly actually, and this is approximately, so we will have 2g times 0.4, so I get 0.8g. So VB square is 1.6g. That will give me VB, and it's a speed, so I'm going to just have plus, not minus also. 1.6g. Note, if I got a minus sign over here somehow, then I must have made some mistake earlier. So I will have to trace back where the sign came from. Because this is square of a square of a number is going to always be a positive number, so that's really a check here. Okay, so this is the answer. And so if I say g is approximately 10 meter per second square, then VB is square root of 16 meter per second, which is 4 meter per second. Okay, how about EC? EC, I really, at C, I don't need to worry much because potential energy at C is 0, because HC is 0. That just means energy at C is just half mvc square. So EC equals to EA, just gives me half mvc square equals mg 2 minus 2 cosine 60 degrees. So again m cancels out. Vc is equals to 2g times 2 minus 2 times, this is going to be exactly half, so this is 1 is 2g. So Vc is equal to square root of 2g, which is, taking g to be 10, is square root of 20, and this is going to be 2 square root of 5 meter per second. Okay, this is how we can apply energy conservation to a pendulum, plain pendulum. This is a plain pendulum problem. I hope you can practice it in more complicated situations. we will do one more example today. Another example we'll do is a car going around a bend. That will be an example of not energy application, but application of force in a more complicated situation. So see you in the next video.